20% of silk fibers are damaged during the reeling of cocoon into silk fibers. These wastes are still good base for making conducting polymers because of their flexibility, large number of active groups, and electronic conductivity. The study aims to modify damaged Bombyx Mori silk fiber through in situ polymerization of polyaniline and optimize its electrical conductivity using response surface methodology by a three-factor, three-level Box-Benken statistical design, determining how the different factors such as concentration of dopant, oxidant to monomer ratio, and soaking time. The 15 experimental trials were conducted with the corresponding combination of the dopant concentration, oxidant to monomer ratio, and soaking time. The 15 samples were washed and dried. After drying, the resistance is measured using a resistance meter, and the corresponding conductivity is computed. Minitab version 17 was used to determine the optimal values using the analysis of variance and the regression formula. 92.7 Siemens per meter is the optimal value of conductivity. Oxidant to monomer ratio and soaking time are the most significant factors in the conductivity, and increasing the value of the dopant concentration can further improve the conductivity. Fourier transform infrared spectroscopy and scanning electron microscopy are used to identify the chemical properties. The SEM image shows that polyaniline appears to be uniformly coated and distributed on the surface of the fiber. The EDX spectrum shows the peaks corresponding to carbon, nitrogen, oxygen, and sulfur confirms the presence of polyaniline, and peak of chlorine shows the presence of p-toluene and sulfonic acid. The FTIR spectra confirms the successful synthesis of polyaniline and the p-toluene sulfonic acid. The material shows good thermal stability with minimal mass loss. This is the safe operating range for sensor applications. The DSC curve shows no significant thermal events, indicating structural stability, wide operational temperature range, and makes it suitable for most environmental and biomedical sensing applications. In order to show the possible application of the optimized spun silk-based conducting polymer, an experiment of ammonia sensing is conducted which shows a positive effect. Conductivity further increased as ammonia vapor is introduced to the fiber. Other applications of spun silk-based conducting polymer are wearable electronics, sensors, and energy storage services.